Hi everyone, my name is Celia Latevsky and I'm a postdoc in Jamie Riley's Concepts and Cognition Lab in the Department of Communication Sciences and Disorders at Temple. I'm really excited to be talking to you today about a new natural language processing R package that we developed to investigate the flow of semantic information in speech or text. Natural language processing is a very large field of computational linguistics and artificial intelligence that involves building large computational language models to analyze massive amounts of language. I will be talking about just a small example of this, and that is what we call semantic flow. So to begin, let's do a quick overview of what we mean by semantic processing. Semantic processing, or semantic cognition, refers to our knowledge of concepts. For example, our knowledge of this cat includes taxonomic or categorical information, such as it being in the Linnaean order of carnivores and in the class of felines, or it having the trait of being fluffy. And our semantic knowledge also includes thematic information, or what environments that concept is found in, or what items it's commonly found with. In the case of a cat, it's often found alongside a meow, it's often found in places where there's litter, and it's often found with a toy. So all of this information, taxonomic and thematic, make up our knowledge of what a concept is, like what the concept of cat is. And most research on semantic cognition has focused on this kind of semantic knowledge. What do we know about individual concepts? But in typical language, we're not just producing or comprehending individual words. We're encountering sentences and paragraphs and discourse. So this is what leads us to consider what we call semantic flow, and that is how semantic information changes over the course of an utterance or text. Imagine you're looking at this image and you use the sentence, "The cat smells the daisy," to describe it. Each of the words in that utterance has its own semantic information associated with it. The word cat is associated with concepts like feline, cute, and fluffy. The word smells is associated with concepts like nose and sense. And the word daisy is associated with concepts like pretty, flower, and colorful. So what we did in our R package is try to capture how the semantics of cat transfers to the semantics of smells and daisy over the course of this sentence or any utterance or text sample. Now, why might we be interested in this? Well, as someone in a clinical speech pathology department, I'm interested in this because I care about language abnormalities in people with atypical language, like individuals with aphasia or schizophrenia. And it turns out that the flow of semantic information is compromised in some syndromes. In typical speech, we tend to stay relatively constrained to one topic and then slowly transfer to different topics. So if I were to tell you the Cinderella narrative, I would start by talking about how Cinderella was a maid for her evil stepmother and stepsisters, then change topics to talk about how she went to a ball and fell in love with the prince, and then change topics again to talk about how the prince found her by matching her glass slipper to her foot. And each of these topics would be about the same general semantic topic and then transfer to a different one. One difference compared to this typical speech pattern is that individuals with aphasia often produce a lot of perseverations when speaking or telling a story, meaning that patients tend to get stuck on the same words or ideas. This example here is from a patient with aphasia telling the Cinderella story, and they say, "Then they go to a ball, and that's why the prince, they went to a date or something, so they went to a ball." And this repetition of the ball is an example of perseveration, and it can be captured if we consider how information changes, or in this case, doesn't change, over the course of an utterance. On the other hand, schizophrenia is often characterized by disorganized speech with large topic jumps. So let's look at this example from an interview of someone with schizophrenia. They say, if you've got someone doing the drugs, we'd say, I don't know what's for real. I know from what I see, but I don't know if it's for real or not. So that's why you see people different. And say like they have an anointing. Sometimes when I come outside, I can see when I look at the trees, the wind starts blowing because we get oxygen from the plants and we give them carbon dioxide. As we can see here, there are a lot of topic jumps. The utterance isn't constrained to a single semantic topic. If we consider how semantics flows over the course of an utterance, we can see these huge topic jumps that don't tend to exist in typical speech. So how do we track this kind of information unfolding over time? Well, the first step is that we need to have some way of quantifying semantic information. This is often done differently if we're considering taxonomic, categorical semantics than if we consider thematic semantics, but both ways typically involve making each word a multidimensional vector. For taxonomic semantics, each word is typically a vector with values representing one of many different characteristics. For example, we might have a binary dimension for animal, vehicle, or clothing, where the word gets a 1 or a 0 if it fits into that category or not. We can also have continuous dimensions like color or smell, which tells us to what extent that word is associated with a particular color or smell. And we can have as many dimensions as we would like for as many categories as we would like. And typically these kinds of vector values are determined by crowdsourcing, where we ask thousands of participants to rate thousands of words along each of the dimensions that we care about. Thematic semantic vectors are often constructed using what are called embeddings. Basically what we do here is select a massive corpora, like a massive database of every single Wikipedia article, and see how often two words are found in similar contexts. For example, I can ask in all of Wikipedia, how often is the word dog found within 10 words of the word leash? In this case, maybe those two words occur together 5,675 times. I can also ask how often is the word dog found within 10 words of the word asteroid? Maybe those two words co-occur one time, and so on. We can do this for every single word pair in the database to construct a massive matrix showing us how often every pair of words is found nearby every other word. Then we can do dimensionality reduction on that massive matrix to boil down each word to a smaller vector, say 100 or in this case 300 dimensions. In this case, we can see that words that are typically found together, like dog and leash, or like planet and asteroid, have more similar vectors to each other than words that are not frequently found together, like dog and asteroid. But we don't want to just look at two vectors' values and see if they're similar or not. We want to quantify how similar or different two vectors are. To do that, we calculate what's called cosine similarity. If we were to plot two words vectors, like kitten and chipmunk on the left here, we could calculate the angle between those two vectors. In this case, I'm plotting just two dimensions, where one dimension represents mammalness and the other dimension represents cuteness. But this would apply identically if we had many, many more dimensions. Once we have that angle, we can calculate the cosine of that angle. And by giving it a cosine value, this shows us how similar or different two vectors are. If the two vectors were identical, like if we were looking at the kitten vector compared to another kitten vector, they'd have a cosine value of +1. And if they were completely the opposite, they'd have a cosine of -1. And you can see in this example that if we had taken the cosine of kitten and robot, we'd have a much more negative value, a cosine value close to -1. Now we can keep our cosine similarity values in the -1 to +1 range, But since we were interested in cosine distance, or how different two vectors are, we decided to flip the cosine similarity value. We instead calculated cosine distance rather than cosine similarity, so that two identical words would have a cosine distance of 0, and two completely opposite words would have a cosine distance of 2. And in this case, two words with smaller cosine distances are more similar to each other, and two words with distances closer to 2 are more dissimilar to each other. So today we're going to go through two tutorials. The first one will introduce our Semdist Flow R package, so you can see how it works to calculate semantic distances in a text sample. The second tutorial will go through some example analyses to show you how you can apply semantic distances to many different kinds of analyses. We'll talk about how to compare the writing of one author to another's, how to relate semantic distance to neuropsychological measures, and how to apply this kind of data to more advanced analyses like time series and network analyses. Thanks for joining me.